Start off explaining what is a modular form. Actually, the first question really should be, can you read my handwriting? Those in the back. Legible? Yes. Okay. Thumbs up. Good. So a modular form is a special type of analytic function on the upper half plane. So there's an amazing picture of the upper half plane. So it's the complex numbers with positive imaginary part, and we're usually going to denote a point in the upper half plane by the letter tau, x plus I, y. Before I can define what a modular form is, I have to introduce one matrix group. So that's the group SL2Z. So SL2Z. These are the 2 by 2 matrices with determinant 1 and integer entries. So the letter S in matrix land stands for special linear group. Special is a funny word that just means determinant 1. So if you picked 4 integers at random, they're not going to satisfy this condition. In fact, if you pick 3 components at random and solve for the fourth number you can solve for, but it probably won't be an integer. So if you want to write down a random element in this group, well, you have 1, 0, 0, 1, not so interesting. But you want to write down a kind of generic example, what you should do is just pick any 2 relatively prime integers. So somebody give me 2 relatively prime integers.
2 and 3.
2 and 3, okay. And so what you can then do is, can you make it slightly more interesting?
5 and 12.
5 and 12, okay. 5 and 12. And so you give me relatively prime integers. If I want this to be an SL2Z, find x and y that fit, well, I just have to solve 5y minus 12x equals 1. And so the numbers are small enough, perhaps somebody can eyeball a solution in integers. Anybody see a solution in integers?
Y equals 5, x equals 2.
X equals 2, y equals 5. And in general, if they're relatively prime, you can find the x and the y using Euclid's algorithm. So there's no lack of lots and lots of examples of matrices. You can write them down. And the reason that this group is going to play a special role is that matrices in this group can be applied to points in this plane to give other points in this plane. So you have an important example of an action of the group SL2Z on the space H, and it's by linear fractional transformations. So a matrix applied to a point in the upper half plane is defined to be A tau plus B over C tau plus D. And so these are examples of linear fractional transformations. So if you take a course in complex analysis, you often study Mobius transformations that are also called where A, B, C, D might be complex numbers, and the tau might be a general complex number. But when A, B, C, D is a matrix with determinant 1, or maybe more generally positive determinant, it sends points in the upper half plane to points in the upper half plane. If you just look at the expression A tau plus B over C tau plus D, why couldn't that be located down here? So it turns out that if tau is in the upper half plane, and this is a matrix with positive determinant, like determinant 1, this is also in the upper half plane. So why is this result also in H if tau is in H? It's because there is a magical imaginary part formula. The imaginary part of A tau plus B over C tau plus D, we hope it's positive, turns out to be if A, B, C, and D are real numbers, and tau is any complex number, there's a beautiful, maybe I didn't call it magical, formula. The imaginary part of A tau plus B over C tau plus D is AD minus BC times the imaginary part of tau over the absolute value, so those are absolute values, not parentheses, absolute value of c tau plus d squared. So I guess we don't want tau to be minus d over c, make the denominator 0. Of course, if tau is in the upper half plane, certainly not going to happen, it's not 0, that's positive. And if the determinant is, say, 1, that's positive. And so what we see then is that the imaginary part is positive if AD minus BC is positive and the imaginary part is positive. So any real matrix with positive determinant by linear fractional transformations moves the points in the upper half plane around. So in particular, integer matrices with determinant 1 move points in the upper half plane around. Okay, so when I took my first course in complex analysis, verifying this equation, this was a problem on the first problem set. I still remember when I saw it, I thought, it's a weird formula. I wonder why he's asking us to look at that. Well, it's a really important formula. Okay, so it's a good exercise to try to verify that's true if you have not seen that before. So, let's now define what a modular form is. I think we'll move over here. So I guess first we have to, modular form depends on a parameter called the weight. So that will, for our purposes, be an integer. So let k be an integer. A modular form of weight k for the group SL2Z. So it's a function on the upper half plane, complex valued function in the upper half plane, satisfying 3 conditions. So the first condition is that it's a holomorphic function or analytic function. It has local power series expansion everywhere on the upper half plane. The second condition, and I'm going to call this the modularity condition, is the following. F of a tau plus b over c tau plus d equals c tau plus d to the k times f of tau for all the matrices in SL2Z and all the points in the upper half plane. So it's explaining how the function transforms points after you apply a linear fractional transformation to them from the group SL2Z. I'm not saying what happens if A, B, C, D are real numbers in general, but it's just if it's a matrix in this group and you hit it on the point tau, the function on that is related to the original function value by this extra funny factor. Now this equation, maybe let me add the third condition and then I'll say something about this bizarre looking equation. I've never seen it before. Like, where in the world would anybody think of that from? The third condition is that when you're in the upper half plane, we're going to be interested a lot in what happens as the points go up, as the imaginary part gets big. And so this is sort of a boundary condition. As the imaginary part gets big, and we'll often write that as tau goes to I infinity, as just a shorthand. I mean, it's getting large by going up, not by going off to the side. The value of the function is bounded. It is never more than 3 in absolute value or something like that. Okay. So, the second condition, example, the 0 function. All right, there you go. Of any weight, you see, it's very versatile. So, not so interesting. It turns out, for some weights, the only modular form of that weight is the 0 function. Okay, so we're really, of course, interested in non-zero examples. But to give examples that are not just the 0 function, or I suppose when the weight is 0, then this factor kind of isn't there, and then a constant function could be an example. There you go, second family of boring examples. So if you want non-constant examples, I mean, it requires some work. Okay, so we'll see shortly some examples called Eisenstein series that are modular forms of many weights. But I want to address the question, like, where in the world would anybody ever think of this strange condition from. It's not like I'm saying, well, it's invariant. I guess if the weight is 0, then you're saying it's invariant. But in general, it's kind of this strange extra factor. So let's take a look at some examples of the modularity condition. So it's an infinite set of conditions. Right? I'm saying for every single matrix, you must have this happen. So what does this mean when the matrix is 1, 1, 0, 1? Or when the matrix is 0, minus 1, 1, 0? Okay? Or when the matrix is minus 1, 0, 0, minus 1. These are all matrices in SL2Z. Okay? So what does the modularity condition mean for those matrices? So when it's 1, 1, 0, 1, and you plug that in, you're saying f of tau plus 1 equals, C is 0 and D is 1, so this weird factor doesn't even show up. You're just saying f of tau plus 1 is f of tau for all points. So the function is periodic when you move to the right. Tau to tau plus 1 doesn't change. The second condition, you plug in 0, minus 1, 1, 0. You're saying f of minus 1 over tau is tau to the k f of tau. Okay? So you can think of minus 1 over tau as a transformation in the upper half plane that if you say, suppose this is the unit semicircle, there's 0, 1, minus 1. If tau is here, minus 1 over tau will be somewhere over here. So it's not 1 over tau. If it were just reciprocation, it wouldn't stay in the upper half plane. But if you negate it, then minus 1 over tau is a transformation. It exchanges the outside and inside of the region divided by the unit semicircle there. So it's telling you how the function value at that point and that point are related. They're related by the kth power of the input, where k is the special parameter called the weight. And then this last condition, something funny happens here. When b and c are 0 and a and d are equal, actually, on the left-hand side, this has the same effect as the identity. It doesn't change it. It doesn't change the number at all, because the minus signs cancel. And so you're saying, and c is 0 and d is minus 1. So what we're saying here is the function is equal to itself times minus 1 to that weight. So if the weight is odd, the function has to be 0. Okay, so we see that if k is odd, that's a minus sign. There's no modular forms of odd weight besides the 0 function. So for the most part, we're going to be looking at modular forms of even weight. You can define modular forms for other groups. And if your group doesn't contain the negative of the identity matrix, and this trick is not available to you, and you really can have modular forms of weight 1 and odd weight for other groups besides this one. But for this group, using a trick with this example, we see that there's no modular forms of odd weight. Okay? So where does, I have, of course, haven't given you any actual interesting examples with the 0 function all the time and constant functions, with the weight of 0, and that's boring. So this condition, I explained in the lecture notes, which will be posted online, that this condition is natural, if it doesn't seem that way to you, from the viewpoint of the developments of the complex analysis and hyperbolic geometry in the 19th century. So it really was, if you had functions that had this kind of property, you could make certain constructions, invariant functions on certain kind of compact surfaces. So there really were compelling reasons to be interested in functions that satisfy this property. All right, so I'll just refer you to the lecture notes so you can read more about the background behind this kind of strange condition. Any questions? Okay, so we want to give some examples, but just before we do that, I had said before that, see, this is an infinite set of conditions. Now, it turns out that the group SL2Z is generated by just 2 matrices, and using that, you can actually convert this. This is equivalent to actually just 2 conditions, right? So let me point out how that works. So for this modularity condition, what you can do, and check as an exercise, is that if this modularity condition holds for a function and two matrices, A, B, C, D, and A prime, B prime, C prime, D prime, then the modularity condition holds for this function and the product of the matrices. And it also holds for the function and the inverse of the matrix. So this condition is preserved under multiplication of the matrices that satisfy it. The set of matrices in SL2Z for a particular function that fit this on the group. For example, the identity 1001 always works. Not so interesting, but what it means then is if the group has this group has some known generators, you actually only have to check this condition for the generators, and it automatically works for their products and inverses and things like that. And so therefore, this infinite set of conditions actually turns into just a finite set of conditions. In fact, two conditions to check, because the group SL2Z turns out to be generated by two matrices, and in fact, I just wrote them down over there on the right, so I'll tell you what they are. And then we'll be ready to give some actual examples of modular forms. So, the fact is that this group, SL2Z, so this is an infinite non-abelian group, this group is generated by two matrices, S, 0, minus 1, 1, 0, which has determinant 1, and T, 1, 1, 0, 1. Okay, so every matrix in SL2Z is a product of these matrices and their powers and inverses. So this matrix has infinite order. Right, powers of the matrix T are pretty easy to write down. S actually has finite order. Okay, S squared is the negative identity, so S has order 4, and T has infinite order. So these two matrices together generate the whole group. And in the lecture notes, I present two proofs of this. You can give a very algebraic proof. We just do some matrix manipulations and reduce, reduce, reduce. But I also give a geometric proof using the action of these on the upper half planes. So let's write down what those are. S of tau, we had it there before, is minus 1 over tau, and T of tau is tau plus 1. So you see how T to the n, you just, instead of adding 1, you just add n, which is consistent with this, tau plus n over 0 plus 1. And so if you use the effect of these matrices on the upper half plane, you can prove geometrically that this group is generated by these two matrices. Okay? So I'll defer to the lecture notes for that. Yes? Okay, so this is a very good question, whether S squared is the identity. What I said over here, you know, if we looked at minus 1, 0, 0, minus 1, its effect on the upper half plane is not to do anything. So there is this distinction, a very mild one, between the matrices, per se, as matrices, and the matrices as transformations on the upper half plane. So if you just think about them as matrices, and that's what I really mean here, this group, everything is a product of these things. The negative of the identity, this is not the identity element in that group. If you go over and look at these as transformations, well, then the negative of the identity acts trivially. And in fact, any matrix and its negative, both have determinant 1, will act in the same way. So as a transformation of the upper half plane, S has order 2. As an actual matrix on its own, has order 4. Okay, so there's this collapsing of the things up to a plus or minus sign. When you look at them in transformation land, then you kind of lose some information. But I don't want to stress this point too much. Some people, when they develop modular forms, will not work with the group SL2Z. They'll work with the group SL2Z modulo plus or minus the identity. So that way, objects in the group really transform in different ways. Right? In linear algebra, two different matrices will definitely not act the same everywhere. Right? At least on 1, 0 or 0, 1, there'll be difference. But on the upper half plane, two matrices act in the same way, in fact, exactly in this group when they're off by a minus sign. Okay? But I don't want to stress that too much. But this definitely has order 4 as a matrix, but it has order 2 as a transformation. Okay? So it's kind of a little minor point, depending on where you read treatments of this. You might be kind of surprised, like, wait, that's not trivial. Well, it's a transformation it is, but as a matrix it is. Okay. Questions? Other questions? No? All right. So I think we're ready to give our first examples of modular forms. So the fact that this group is generated by these transformations means, so I'll erase, well, I'm erasing the conditions here, but in fact I think I'm just going to write them down again. So what that theorem tells us is that to check that a function is a modular form, of some weight, it suffices to check the first condition, the third condition, and instead of checking this condition for all of SL2Z, we'll call this 2 prime, you just have to check the modularity condition for the matrix T and the matrix S. Okay, so those conditions I wrote down before, I'm writing them down again. If the function has that property for the matrix S and T, then it has it for their products and so on, because this condition is preserved under matrix multiplication and inversion. So we only have to check 2 conditions since the group is generated by those 2 elements. All right? I'm not saying it's obvious that this condition behaves nicely under multiplication matrices, but it's a calculation you can make. I think I wrote it up in some form in the lecture notes that will be posted later today. So if somebody presents us with an example and says, is this a modular form, we can just try to check these 2 conditions. Okay? So let's now give our first example of modular forms that are interesting. And so these are called Eisenstein series. Eisenstein series. So perhaps you've heard the name Eisenstein in some other contexts, namely irreducibility. Right, Eisenstein irreducibility. I remember through college I thought, is that all the guy ever did? It's the only thing you ever hear about. Well, no, he did other stuff. I mean, he died at a young age. He didn't do too much compared to how much he could have done. But this is probably much more significant than the old Eisenstein irreducibility criterion. Same person. And so what we're going to do is, it's a construction that gives examples of non-constant modular forms of any even weight bigger than or equal to 4. The construction doesn't work when the weight is 2. In fact, it turns out that the only modular form of weight 2 is the 0 function, although that's not so clear as it is for the odd weights that we saw before. There's no easy trick to show that. But for weights greater than 4, we have a construction of examples. And so if k is an integer, even number that's at least 4, here's what we're going to do. We're going to define g sub k of tau. I don't know why it's the letter G. Eisenstein's first name starts with a G, so maybe that's the reason. Who knows? So gk of tau, it's an infinite series. So it's a sum over all integers besides 0, 0. Don't want that. 1 over n tau plus n, all to the kth power. Okay, can you see that in the back? Yeah. Okay, so it's an infinite series, and we want to check, see why it satisfies the conditions that define a modular form. So we need to check that it's holomorphic on the upper half plane. We need to check that it satisfies those 2 conditions. Its value at tau plus 1 is its value at tau, and its value at minus 1 over tau is tau to the k times its value at tau. everywhere on the upper half plane, and we need to check that the function is bounded as tau marches up to infinity. So these are the conditions that we want to check. So strictly speaking, the first thing one needs to check is that the series converges. Before you worry about whether it's holomorphic, does it even make sense? So I'm gonna focus on the second condition, but I'll say things about the first one. So I mean, this is a genuinely analytic statement. One has to somehow have a reason to know why these things are convergent and why should it be holomorphic. So maybe I will make sure it works. So the first thing to say is that the series converges absolutely since that exponent k is bigger than 2. In the lecture notes I explain in some general sense why such sums are always going to be absolutely convergent. And anytime a series is absolutely convergent, it means that you can reorder the terms and it doesn't affect the value, okay? Which is certainly convenient when you have a sum over a doubly indexed set. Oh, what's the order? It doesn't matter. It's absolutely convergent. You can sum it in any order you wish. Now, just because it converges, why does that mean that it's an analytic function of a complex variable? So you have to go hunting around through your book in complex analysis and say, where is there a theorem that would tell me that an infinite series of analytic functions is analytic? Each term is analytic. Should that mean that the whole series is analytic? Well, you're going to wave your hands, but there is a real condition that would verify this. So the series converges uniformly on compact subsets of the upper half plane, and so that means that if you take the upper half plane and you draw some compact set, closed bounded set, that because we know that the thing makes sense, since it converges absolutely, it converges, the difference between the series and the partial sums can be controlled and get uniformly small everywhere at the same time across the entire set. So the series converges uniformly on every compact subset, and there's a fundamental theorem in complex analysis that any sequence of analytic functions on some region in the plane that converges uniformly on compact subsets of the plane has a limit function that is itself holomorphic. This is false in real analysis. The absolute value function for -1 to 1, it's not analytic, got a little bit of a problem at 0, but it can be uniformly approximated by polynomials. This is the Stone-Weierstrass theorem. And polynomials are pretty analytic objects, right? Very simple. So it really is a special feature of complex analysis that we can derive analyticity from uniform convergence of compact subsets. So that's all I'm going to say about this, that there are theorems that guarantee that this series is itself analytic. What about the modularity conditions? So we're going to use the fact that the terms in the series can be rearranged. So if we replace tau with tau plus 1, what happens? We get 1 over, let's see, m tau plus m plus n. And so what we see here is that instead of summing over m's and n's, if we sum over m's n plus n's, I mean, this is a pair of integers that's not 0, 0. Exactly, this is a pair of integers that's not 0, 0. And so this sum is summing over these pairs of integers that are not 0, 0, but that's the same set overall in a different order as pairs m, n that are not 0, 0. And so thanks to absolute convergence, we can reorder the terms, and with a different meaning for m and n, or at least a different meaning for n, we get the series back. Okay? So we satisfy the first condition, the first modularity condition, And what about the second one? So for the second modularity condition, it's going to be slightly more interesting. All we have to do is just compute the terms and then do a little bit of algebra, and we're going to see the extra factor of tau to the k popping out. So let's do the calculation. If you use minus 1 over tau, again, remember, tau is big, minus 1 over tau is small, and vice versa, in the upper half plane. So if we have pairs of integers that are not 0, 0, 1 over m minus 1 over tau plus n all to the k, let's see, without changing the terms, I'm just going to put a tau to the k on the top, and minus m plus n tau to the k on the bottom. Okay, so I haven't actually changed the terms at all, just rewrote them. But again, let me take the tau to the k out. So now you see how the factor tau to the k popped out. We understand now why in the definition the exponent k is important there. Take the tau to the k out, and then we have n tau minus m to the k, and not 0, 0. And again, by just rearranging the terms, this is exactly the same definition as before. It's just my old m and n has now become n and minus m. And so just by swapping the pair mn with this pair the pair n minus m, again, not 0, 0 is the same as not 0, 0. We can just rewrite this. It's just the order of the summation doesn't matter. Whoops, forgot my factor there. And we get our Eisenstein series back with this extra factor of tau to the k. Okay? So this has given us an example of a modular form. Whoops, not quite. I want to check the behavior at infinity as tau gets big. And again, this is a serious analytic issue. How do you study the behavior of this series as tau gets large? So I will suggest how to think about this. I'm not going to go into the details too much. So can we figure out how this behaves? How does this series behave as tau gets big? Well, if we're going to wave our hands, then as long as n is not 0 for each individual term, as tau shoots off to infinity, this will go to 0. If n is 0, well, the term is just 1 over n to the k. It doesn't matter what is happening with tau. So it appears that as tau gets large, if we're willing to believe that term-wise limit calculation is justifiable, it seems that all we're left with is the sum of 1 over n to the k, where n is not 0. So let's write out the series by isolating those terms. So let's first break off the terms where n is 0. If n is 0,